I'm gonna close that blind behind me before I start. Wait, my mouse is in the wrong place. That's fine. What? La ti 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 ti. Okay, I'll have to open this application. Go here, and my internet's not working. Okay, and my internet is working. And there you go. Here, and the stream is working. Oh, it says it's live.
He's a fucking little scumbag, just like you. That video of him driving, you little bitch.
Okay, let's turn that off. Anyone else joining?
He's a fucking little scumbag, just like you. That video of him.
Okay. We have one person. Yippee!
Hi.
Hello. So let me just screen share this one. I'll just wait for a couple more people to join. I feel like I'm gonna. Okay, we got Salam. Hey Salam. By the way, this is being recorded, guys. So, anything you wouldn't do in a recording, don't do it now. Let me just screen share. This one. Oh. So has everyone's holiday started? Okay. Hey Joe.
Yeah, how you doing, bro?
Pretty good. I'm just gonna say this now, Joe. This is being recorded, so if anyone wants to watch it back later, you can, but just be mindful because it is being recorded.
Oh,
Yeah,
yeah, okay.
don't say anything that you wouldn't say on a recording, basically.
Alright.
Okay. So, oh wait, one class, one group of people, Oh, meant to be the other one. So, how many of you are familiar with organic?
A little bit, yeah.
A little bit?
Yeah, same.
Yeah, same. What about you, Blessing?
Yeah, a little bit.
A little bit. Okay, so all of you have a little bit of familiarity, which is good, right? Because it will help a decent amount with this. Because the majority of this first part is just going through the basic understanding behind organic, right? It's not doing anything crazy, yeah. So it's not like, oh yeah, look at all this stuff. It's just like, okay, this is how we're gonna begin organic, and it's mostly just focusing on nomenclature. Do you guys know what nomenclature means? Anyone know what nomenclature means? Anyone want to call it out?
Nope.
No, okay. It's just the naming convention that we use for things, so that's what nomenclature is, right? The other thing that we're gonna be dealing with is more or less just being able to identify, or is this an aldehyde? Is it a ketone? Is it like, or is it like something else? Yeah. And now the first thing I need to ask all of you is, do you have your best friends in front of you?
What, data book?
Yeah, your data book.
Yeah, I got it.
Okay.
Yeah.
Yeah. Do you have yours, Blessing?
Yeah.
Okay, perfect. So we all have the data book, which is good. I was expecting one more person to join, but it's fine. We'll start anyway. So this is a list of definitions. Now, you don't need to know any of these definitions inherently. We'll be going through all of them. The only one that like really can't like that you'd really know here is maybe the idea of electronegativity, right? Everyone here is aware of the electronegativity and how the electronegativity trend works,
Yeah, I do.
as well as maybe the idea of the terminal carbon, which we'll discuss a little bit more. You know, if we have this is our compound, for example, this is all of you guys know that this is ethanoic acid, yeah. Obviously, we'll deal more into it, but the terminal carbon will be this one, yeah. So that's the last carbon. Any questions about that?
Nah, not right now.
So this is more or less just a whole. This is just the stuff we will be going through mostly. That's the whole idea behind the definition. It's not to scare you, yeah. So, this first slide is just talking about what like what makes carbon good, and they're not going to focus on this one too much in VCE chemistry. This is more or less for the sake of completeness. Yeah, it's the idea. Well, the three ideas that we have here is the number of valence electrons. So you guys all remember that there's 4 valence electrons on carbon, which allows it to produce many bonds, right? The other thing is the relative strength. You don't need to know about strength anymore because they actually took this out of the data book, right? So they had the. Do all of you guys have a copy of the 2025 data book? If you look in there, probably table 9 and 10, they're going to have the bond strengths. They've taken that out now, so you don't need to know that. And that idea of the bond strength also goes into the idea of the stability of the bonds, right? If you have stronger bonds, they're going to be more stable. That's an implicit thing. So any questions about that at all whatsoever? Nothing? Okay. All right. So this just goes through like explaining the different ones. Now, the idea of saturated and unsaturated is something that we're going to need to know for later. So when we start doing pathways as well as tests, yeah. So the saturated focuses only on carbon-carbon single bonds, yeah. So for example, these two here are oh wait no. So this one here is considered a saturated molecule because it only has carbon-carbon single bonds, yeah? This one is also considered saturated. Even though it has a carbon-oxygen double bond, that doesn't mean it's unsaturated, okay? Here, this one here and this one here are both unsaturated because they have carbon-carbon double bonds and carbon-carbon triple bonds, yeah? So does that make sense? Does saturation make sense? It's just talking about is there carbon-carbon double bonds or triple bonds? Yeah. Now we'll talk about after we deal with the benzene rings, we'll talk about the idea of the degree of saturation. But does that all make sense? Okay. You guys got like an indicate. Give me like a thumbs up. You know, you have like the thumbs up thing here. You have so many emojis to choose from, like the, you know, yippee hooray. I don't know. Okay, thanks, Joe. So we'll move on to the. Oh yeah, so this just goes through the different types of bond strength. We'll talk more about the idea of the polarity with polarities, but the big thing that I'll probably focus on here is just the electronegativity. So as you guys might remember, the electronegativity increases as we go across the periodic table, and also increases as we go up the periodic table. So we all know that nitrogen, oxygen, and fluorine will produce highly electronegative bonds, right? Compared to something like lithium. So our main things that we're going to be dealing with here are going to be carbon, nitrogen, oxygen, fluorine. There might be some other halogens like chlorine, bromine, and iodine, but we'll deal with them once we get to them. Yeah. And those will be the main things that make up our bonds. So basically, right, we're dealing with either like very non-electronegative molecules or very non-polar molecules, or we're dealing with very polar molecules here. Yeah. So I just want you to get that out of the way. So like for example, we have this is considered a polar bond, yeah, because here we have a very strong electronegative molecule, fluorine, bonded with carbon, right? So here, what it means to be electronegative is that it pulls it towards. Now, you don't need to get too fussed about this. It's more or less that if there's like a carbon bonded with a fluorine, it's going to have a polar bond. If it's a carbon bonded with a nitrogen, it's going to have a polar bond. If it's a carbon bonded with an oxygen, it's going to have a polar bond. Yeah. However, carbon bonded with hydrogen is going to be a non-polar bond. That's the thing I want you to remember here. Yeah. So basically, everything is a polar bond unless it's carbon and hydrogen. Like here, carbon and chlorine, they're also polar bonds. So any questions about that? Thumbs up. Yeah, repeat. No. What don't you understand, Joe?
No, that just means I don't have any questions, man.
Oh, yeah. Okay. My bad. My bad, gang. So here it says, which one of the following affects the bond strength? Yeah. So here, does the length of the bond affect the strength? Just give me a thumbs up or a thumbs down, please. Length of the bond. The length of the bond. So this is why I probably shouldn't have skipped this. It does. So bond length, electronegativity, and atom size. So think about it. If they're further apart, they need more energy to be held together, right? So they're less stable. The other thing is the atomic length actually increases the bond length. So do you guys remember your what's it called? The the radial lengths at all of bonds? Give me like a
Whoa, remind me, was it something like the bigger the atoms, wait, so what happens again? I forgot.
Yeah, so as we go to the right of the electrochemical series, the bond the radius of the bond, or the radius of the bonds that an atom can produce, will reduce. So for example, fluorine has a smaller radius than, let's just say, lithium. Again, because it's more electronegative, there's more protons to pull in. Yeah, all good. Okay. So here, right? Bond length does impact it. Yeah. Does the atomic number affect it at all? What does the atomic number say?
Was it the amount of valence electrons, kinda? Yeah.
So the atomic number tells you the number of protons. Yeah.
Oh yeah.
Remember, it tells you the number of protons. This doesn't affect the bond length. Yeah. And here the electronegativity, of course it does. The electronegativity means that they're pulled more towards what's it called? If it's more electronegative, it's going to be a stronger bond because the electrons are being pulled more towards one. Yeah. So here, answer option is going to be D. Any questions about that? Is that all good? Okay. So, which one of the following statements is incorrect about carbon atoms? They typically form stable bonds. Is that correct? Give me some sort of perfect thumbs up. Yeah, they do. Here they typically form weak chemical bonds. Is that correct? No, yeah, that's right. That's wrong. So that means B is our answer. Obviously, we know that it produces 4 bonds because it has 4 valence electrons. And here, carbon-carbon double bonds contain a relatively large amount of energy. Again, that's what makes them so stable. Yeah? So, we'll move on to this one. Now, we have 4 different types of formulas that we need to know in chemistry. We have our structural, skeletal, right? Structural, skeletal, semi-structural, and empirical, and molecular. So we have those 5 that we need to remember. Yeah. Here, structural shows every bond, right? For example, with this atom here, this isn't a structural. If I just had OH here, that's not structural. Yeah. Structural needs to show every single bond. Yeah. Here for skeletal, it omits the carbons and the hydrogens bond, like the carbon and the hydrogen bonding, and it draws these carbons in a way that just makes them look like little dots. So here, this molecule and this molecule are the exact same. They're just represented in 2 different ways. So these 4 dots here represent the carbons that are present. Does that make sense to everyone?
So it just skips the carbons in skeletal formula.
Yeah,
That's it.
it just skips the carbons and just makes them
Okay.
just little dots. Yeah. And the only thing that we show here are the extra functional groups, which we'll discuss more later. Does that make sense to everyone? Blessing, does that make sense to you?
Yep.
Okay. Then we have the semi-structural formula. It's essentially, or condensed formula, essentially just condenses it. So, for example, with our previous example, right, if we wanted to write the semi-structural formula here, we have CH3, right? So that's the first thing. Then we can do CH2, 2, which represents these two things here. And then we have COOH. Does that make sense? We can also write this as CH3, CH2, CH2, COOH. They're equivalent to one another. There's no difference between those two. Any questions about that from anyone? Okay. And then the molecular formula, all of you should be relatively aware of the molecular formula. It's just, you know, how many carbons, how many hydrogens. It's the most simplified form. And then the empirical formula is the smallest ratio. Yeah. So in this previous one up here, this has a, like, the hydrogens, the carbons, wait, the carbons, the hydrogens, and the oxygens have a 4:8:1 ratio. Here, I mean 2 ratio. We can simplify this ratio into 2:4:1. Yeah. And that's what the empirical formula shows. It shows the most simplified ratio. Yeah. Any questions about that? Anything from you, Salam? Is that all good for you?
Yeah, all good.
Yeah. So most of you guys should be relatively aware. So here, what type of chemical formula used in VCE chemistry provides the most information about a compound?
I reckon C.
Yeah, C. I should have just been like, as A, B, C, or D. Yeah, no. That's all good, Jeff. Here, right now, we're going to start focusing on the different types of functional groups that we have. The first thing we have is the alkane. Yeah, alkane's very simple. It's just a hydrocarbon. Yeah, it will look something like all hydrocarbons will look like this. So here, this one here is propane. Yeah, this one over here, we'll deal with the naming conventions, and we'll deal with the naming conventions a bit later. But this one is 1-methyl propane. Yeah. And here, these are distinct in the sense that they only have carbon-carbon single bonds. Yeah, that's the characteristic that makes them alkanes. And we can use this general formula to write any alkane out. So for example, if we have 4 carbons, right, that means our alkane we have is going to be C4H10. Does that make sense? So this is our first homologous series. Yeah? And a homologous series, there's a couple of things for homologous series. It has similar chemical properties, similar general formula, same functional groups. Yeah. So those are the things you want to remember for a homologous series. So this is the first homologous series that we deal with. Yeah. So similar chemical formula, similar general formula. Yeah. Those are the two things that we want to remember there. So then we move on to alkanes. Alkanes have a carbon-carbon double bond. Yeah. So here we talk about degree of saturation. So if we have one carbon-carbon double bond, that causes a degree of saturation of 1. If let's just say there was 2, let's just say we took out this hydrogen, there was 2, this would have a degree of saturation of 2. Yeah. So that's what a degree of saturation is. There's another thing that we'll talk about when we talk about degrees of saturation. I'll bring it up when we come to benzene and cyclomolecules. But that's what a degree of saturation refers to. And we refer to it using we use this general formula to find all of our to find out any alkene. Any alkene should abide by this formula. And the last thing is this idea. Now before anyone laughs, before anyone gets any ideas, yes, they are kinky chains. Okay, we'll just get that out of the. Okay, thanks, Joe. No problem. But yes, they are kinky chains. I know Salam, your teachers will bring that up a lot in school. Miss Allenson always brought it up for us. But essentially, what a kink does is it causes a bend in the change. So before with our what are they called? alkanes, we would have just had a straight molecule, right? But for alkenes, right, do you see how there's a bend here? Yeah, there's a bend caused by this carbon-carbon double bond. Does that make sense to everyone? All good? Is that all good for you, Blessing? Okay, perfect. What about you, Salam? Alright. My bad. I'm just like checking up, making sure I don't like go through anything without you guys understanding it. So here, which one of the following structural formulas may represent an alkane, right? So here, is it answer option A? Remember those formulas that I showed you? So answer option A? No? No? Salam says no. Anyone else? Anyone else says no? Joe, what do you think? No? Okay. So it's not that. It's not A. Is it B? B. Salam says no. Yeah. Perfect. What about C? So yeah. The reason being is because here here alkenes follow the formula CnH2n. So because N is equal to 3, we should expect 6 carbons. All of these ones are alkanes because they abide by the formula 2n H2n plus 2. Yeah? Any questions about that? So I'll keep moving on. And if there's nothing else that you want to ask about it. So, cyclomolecules. They don't tend to ask this too much, but here a cyclomolecule is essentially just like a ringed compound. So here, right, this is what we call cyclohexene. It has 6 carbons, which makes it a ringed compound. Yeah. Another one we can think of is, let's just say, this here would be cyclopropene. Oh wait, propane. Yeah. Because it's got it's got no terminal carbons. It goes in a ring, basically. That's the whole idea behind these. And they have no terminal carbons. Now, the textbook mostly focuses on cyclohexene because you don't actually need to really know the naming convention for cyclomolecules. It's more you just need to understand what a cyclomolecule is, and it abides by the same general formula as an alkene, yeah? So if they were to give you a cyclomolecule, they'd have to give you more information about it. Yeah? So remember that they need to give you more information, like because here alkenes and cycloalkanes have the same formula. They need to give you more information to discern the two. Now, here I want to go into another discussion. Any cyclomolecule immediately has a degree of saturation of 1. The cyclical nature causes it to have a degree of saturation of 1. Does that make sense? So I'm just going to make that a rule, yeah? It's double bonds, triple bonds, and ringed compounds cause degrees of saturation, yeah?
So do you reckon that's gonna be the info they give you, or does alkene somehow have like the same thing too?
That probably won't be the thing that they give you. If they were to give you something, it might be, here, this is the formula of it. It doesn't react with bromine. Suggest an answer. And like here, you're probably like, well, why bromine? Salam might already know this from the bromine water test. Yeah, do all of you guys know what the bromine water test is? The bromine water test tests if this is an alkene that we're testing. Yeah. If it doesn't react, that means it's not an alkene. It could be a cycloalkene then. Yeah? So, do you know what the bromine water test is, Blessing?
No.
We'll discuss it tomorrow, yeah? So don't worry too much about it. But the whole idea is that it will give you more information. Now, benzene. This is 3 depictions of benzene that they'll show you, right? Again, you don't really need to know the naming convention for benzene. It's more or less just understanding what benzene looks like. This is a benzene, this is a benzene, this is a benzene. Some people, you might see like videos online about happy benzenes and sad benzenes, but the whole idea is that all of these are benzenes. Now, I'm just going to ask you guys, just type in the chat, what do you believe the degree of saturation of this molecule is? Yeah? Is it 1, 2, 3, 4, 5, 6, 7? Give me an idea. So if you prefer messaging it directly to me, you can. If you are fine with degree of saturation of 3, what do you think, Joe? 2 or 3? Okay. What about you, Blessing? What do you think?
3.
3? Okay. All of you got it wrong. I'll say that now. Don't worry, Salam. This might show up in your sack, but this is 4. Remember, all cyclical molecules automatically have a degree of saturation of 1. Yeah. These 3 double bonds add 3 more degrees of saturation, or sorry, degree of unsaturation. So this is actually has a 4th degree of unsaturation to it. Yeah. Because it's cyclical and it has 4 bonds. I had to search this up myself because I remember that Evo gave this to me on one side and I was like, fuck, why didn't I get the answer right? Everyone got it wrong, don't worry. But like, if you get it right, he'll be like, you're cheating. And then you'll be like, nah. Anyway, and the big thing about benzene here is that benzene simply follows the formula C6H6 again, whereas our cyclohexane follows the formula C6H12, as we remember from before. So now looking at this question, consider the skeletal formula for cyclohexane and benzene. How many hydrogen atoms are present in cyclohexane and benzene respectively? So is it answer option A? Is it answer option A? Does anyone think it's answer option A? Any takers? No? Salam? What about you, Joe? No, from Joe. What about you, Blessing? No from Blessing. So it's not that. What about B? Anyone taking B? Salam's not taking B. Joe's not taking B. No one else taking B. Is Blessing taking B? No, no B. What about C? Anyone taking C? No, no. Wait for one more person. No. Yes, it is. It's D. It's D. Right? It's D here. So, as we remember, this one has the formula CnH2n. It's hexene, so that the hexene means 6. Yeah. This is like a little bit. This is pre-knowledge from last year, but we'll go over this again. Yeah. And then, as we remember, benzene C6H6. Yeah. Cyclohexene C6H12. Any questions about that? So we have the haloalkenes. Yeah. Haloalkenes, simply, they're just like, they just add a halogen group on. Yeah. So here we see that this is a regular alkene, but instead of having a hydrogen down here, it's replaced it by a halogen. Right. So here they've replaced it with the halogen chlorine. Yeah. Sometimes they could replace it with like an iodine, for example, or maybe a bromine. It doesn't really matter. All of them are classified as haloalkenes. Sometimes what they'll do is that they'll draw a molecule. They'll draw a molecule out and they'll put an X here. X just represents that there's a halogen present, yeah? So X, in all of these cases, just like how they've done over here, just means it's present. And here, this is what we call a polar bond, right? Because all the halogens have a stronger polarity than a carbon does. So that means the electrons will be pulled more towards it. So it's now a polar bond. We need to remember that for later when we deal with bonding. Yeah? Any questions about that? Nothing? Okay. So here, which of the following is correct, which is incorrect about the structure of halogens? Halogens are formed by replacing one or more hydrogens in a carbon chain with a halogen atom. Is that true? That's not true. Why do you think that's not true, Salam?
No, I meant like thumbs down, as in it's not the right answer.
Oh, okay, it's not the right answer.
Yeah.
So it is true. Yeah. So it can be one or more. Like before, like they showed us only one, but we could have it look like something like this. Yeah, where we have 2 chlorines instead of 1. Here, the carbon halogen bond is a type of in a halogen is polar. Is that true? Yeah, it's polar. What do you think, Joe? And Blessing. Yeah, that's true. Yep. Okay, perfect. The position and the number of halogens are the same for each halogen compound. Is that true? Have we talked about position whatsoever? Yeah. No. And there's three types. There's branched. Uh, technically you don't know this, but because this is flat out wrong, right? This has to be incorrect. Yeah. So this is where sometimes even if you don't know what the right answer is, you still can find out what the correct answer is. Yeah. Or we can eliminate answer options to find out what the correct answer is. So here we have amines, right? Before we replaced a a hydrogen with a carbon, now we're replacing it with an amine group. An amine group contains NH2 and it looks like this, yeah? They're very polar, yeah? I want you to remember that. These are very polar bonds. And the main reason is because hydrogen has a very strong polarity compared to hydrogen, but these two hydrogens and this carbon over here. So hydrogen would be considered highly electronegative, yeah? Have a high delta negative. So any questions about that? Is that all chill? Okay. So here, then we move on to this idea of primary amides. Yeah. Before we were replacing a hydrogen with an NH2. Now we're replacing a hydrogen, right, with this functional group here. So this whole functional group is called an sorry, not that part. This whole part of the functional group, ignore this hydrogen down here, yeah, is part of that function. It is part of the functional group. So let me just erase it all. It's going to be this whole part here, yeah. That's what we consider the amide bond, right? This is called an amine linkage, yeah. So an amide linkage, yeah. Before we were looking at an amine functional group, yeah. Now we're looking at an amide linkage. Any questions about that? And here we talk about primary because it's on the first carbon, yeah? All amides that we deal with right now, for now, are going to be primary. Later we'll look at some secondary ones. So any questions about that? Okay. So here, which statement is true about the primary structure of amides? The oxygen and carbon in the amide functional group is directly bonded to the carbon. Is that true? Yeah, so that one looks like it's true. We'll have a look at the other one. So here we know A is true. Here it says the oxygen in the amide functional group is directly bonded to the hydrogen carbon. No, that's completely wrong, right? Remember, the functional group looks something like this. So that's not going to happen. The functional group of an amide is CO. No, we know that it's going to look like this. And the nitrogen atom in the primary amide functional group is linked to 3 alkene groups. Well, no, like here it says 3 alkene groups. It's bonded to a hydrogen, right? A carbon, and another hydrogen for the time being. Yeah, we'll talk about it later. It will move on to something else, but right now we're just thinking about it as a primary amide. This is primary. Yeah. Any questions? No. Consider an organic molecule. An organic compound with a molecular formula of C5H13N. Is this compound a primary amine? Right. So no, it does not contain any amine. Yes, it contains amine functional group. Yes, the nitrogen atom is bonded to a terminal carbon. This cannot be determined based on the information. So which one is it? A, B, C, or D? What do you think? Type it in the chat. Give me your answers. B? Okay. What do you think, Joe and Blessing? Salam's carrying everyone here. Any ideas? Yeah, my brain's So here, the answer is D. And it's because of this phrase primary, yeah? We haven't talked about it too much, but the phrase primary, so this is what this molecule will look like, yeah? Primary means that it will occur on the first carbon, yeah? If it's primary, it occurs on the first carbon. And what primary means is essentially, yeah, it is bonded to only 1 or 0 carbons. That's what primary means. Secondary, right, it could be here, yeah, where it's bonded, where the carbon, the functional group is bonded to 2 other carbons, yeah? So it has 2 other adjacent carbons. If we had tertiary, for example, tertiary would be, well, here we have the carbon that is bonded to, right? This carbon is bonded to 3 other carbons. So that's what tertiary refers to. So here, we actually can't determine whether it's a primary amine, right? We can determine that it's an amine, sure, but we can't determine if that's primary or not. We'll deal with this idea of the primary, secondary, and tertiary when we move more into alcohols as well, because you need to know the primary, secondary, and tertiary ones. But we'll come back to this. We'll make sure we'll come back to this. So here, speak of the devil, right? We're just talking about primary, secondary, and tertiary. So here, right, we have hydroxyl group, which makes up the alcohol, yeah? And here, right, this represents it's a primary alcohol, yeah? It's a primary alcohol because it's either bonded to 1 or 0 carbons, yeah? So the adjacent the carbon that's bonded to the actual hydroxyl group, right? The hydroxyl group is bonded to this adjacent carbon, yeah? Over here, this one's secondary because the carbon that the hydroxyl group is bonded to 2 carbons. Over here, this one's tertiary because the carbon, which the hydroxyl group is bonded to 3 carbons. So any questions about that? Joe, did your brain turn back on, or is it still off? Alright, he's still thinking. Do you have any questions, Joe? No? Okay. What about you, Blessing?
Good.
Say it again? You all good?
All good.
Okay. So here, which one of the following represents the structure of a primary alcohol? So, is it answer option A? Give me a thumbs up or thumbs down. Give me a thumbs up or thumbs down. Yeah, thumbs down, thumbs down, thumbs down all around. Yeah, there's not even a hydroxyl group here. I would have been very disappointed in you guys if you said that. Is C a primary alcohol? Alright, so we have 1 thumbs up. What about everyone else? Thumbs up from Salam. What about you, Blessing? Thumbs up? Yes, thumbs up. Perfect. So this is the answer. So C is the answer. B isn't a primary alcohol. It's a carboxylic acid. And D doesn't even contain any. D doesn't actually contain any. So again, we'll talk more about the carboxylic acids. Yeah. So now we have aldehydes and ketones. Yeah. So aldehydes and ketones have the exact same functional group. They have a carboxyl group, and that's just the C double bond O. Yeah. That's what a carboxyl group is. In the VCE now, in the data book, what you'll see is that they call them a ketone group and an aldehyde group. I think you can still use the phrase carboxyl group, but because they put it in the actual, like, our best friend, just call it the ketone group or an aldehyde group, yeah? So here, right, this is an aldehyde, yeah? The reason it's an aldehyde is because it's on either it's on the first carbon. So here, for example, this compound here. This compound is what called... This compound is called butanal, yeah? And the reason it's an aldehyde is because on the first carbon here, we'll have a what's it called? A carbonyl group, or a aldehyde group, as we're going to call it, yeah? This one down here is a ketone because it's not bonded to the first carbon. The carboxyl group is, the carbonyl group isn't bonded to the first carbon. It's bonded to a middle carbon. So for example, we went back to this compound, right? We took out this hydrogen here, and we changed this hydrogen down here for an oxygen. Put hydrogens here. This one would be propanone, yeah? We'll talk about the naming convention more. I just want you to be able to recognize that this is a ketone and that this one over here is an aldehyde, because this one's bonded to the first carbon, yeah? Whereas this one down here is bonded to a middle carbon. Any questions about that? Thumbs up all around. Maybe? Just getting freaking aired out, bro. Let's see if this is still working real quick. Yeah, this is still working. So, here, which statement is true about the structure shown? Both are aldehydes, both are ketones. Structure 1 is a ketone and structure 2 is an aldehyde. Structure 2 is a ketone and structure 1 is an aldehyde. Which one of these is true? So give me an A, a B, or C in the chat. In the chat. So Salam said C. I should get like a private messaging. So I should move this over to Zoom. I don't even know how to do it. Anyone else? Everyone agree with Salam? Give me a thumbs up if you all agree with Salam. Blessing, do you agree with Salam? Okay. So here it is answer option C. Any questions about that? Okay. Now, carboxyl groups. Yeah, we have a carbonyl group and a hydroxyl group. They come together and they form a thing called a carboxyl group. Again, you don't need to remember the name, it's in your data book. Yeah, all of the names are just in your data book. Yeah, so carboxyl group. And here, all of you guys have seen carboxylic acids. This is the first thing that I spoke about before. Here, this is a carboxylic acid. This is going to be ethanoic acid, right? We'll talk about why it's ethanoic acid in a bit, right? But it's an ethanoic acid because it's got this carboxyl group here, yeah? And that makes it a carboxylic acid. Any questions about that? Okay. So here, which one of the following semi-structural formulas represents a carboxyl group? Is it answer option A? So, got a yes from Salam. Do I have a yes from everyone else? Yes, yes. Yeses all around. Perfect. We get answer option A is the answer. This one here, right, has an OH group. So this one would actually be an alcohol. This one down here is most likely going to be an ester. Yeah? We'll talk about, we haven't spoken about esters yet, but this one is most likely going to be an ester. And this one here is going to be a ketone. Yeah? Does anyone have any questions of how I figured out this one was a ketone? I'm not too worried about this one right now. Does anyone want to ask why this is a ketone at all? No? If it's no, thumbs down. If it's yes, thumbs up.
Alright, why is it a ketone?
If I draw, so let me draw this one out. So we have here C, 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 and C. So I'm going to turn this into its full structural formula. So here we have the H, 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 right? We know that there's an oxygen bonded to it, so I'll just leave it as one here. H, 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 and H. So this is what it looks like. This oxygen has to have a double bond because all carbons must have 4 bonds and all oxygens must have 2 bonds. Do you see how the carbon is in the middle, Joe? Oh, okay. So that's what makes it a ketone, yeah? If you can't tell that by just looking at it, always draw it out. If you're ever in doubt, draw it out. Trust. It rhymes for a reason. Anyway. Esters. Esters are... So this is what we call an ester linkage here, yeah? So do you see I'm focusing more on the diagram and not like as much on the words? So that the words are there more or less to help inform you a little bit, yeah? But here, this is the functional group we're looking at. And this one is called an ester linkage, yeah? So you can either call it an ester linkage. I think ester group is accepted, but I just call it an ester linkage because I know that one works for certain, yeah? And here, this one is an ester because it's got this linkage on it, yeah? So it sort of connects 2 chains together. That's how you can sort of think of an ester. Connects the 2 chains together. And why it's got fruit here is because one way we can determine if something is an ester, or like determine if we've produced an ester, is because if you smell an ester, it has a very strong scent. So for example, like synthetic smells of pear or synthetic smells of pineapple might be produced from esters. Yeah. So that's what this is saying. That's why we have this, and it's a sort of test to just see if there's an ester present. We can smell it, and we can say to ourselves, "This smells like an ester." Yeah. Any questions about that? No. So, which one of the following semi-structural formulas would represent an ester? Assume the molecule contains only one functional group. So assuming it only contains one functional group. Here, would this one here contain an ester? Salam says no. Anyone else says no? This one says no. What about you, Blessing? What do you think? No? Perfect. This one here would be a carboxylic acid, right? If I drew this out, this one would be a carboxylic acid. What about this one here? Is this an ester group? So Salam says yes. Said yes. What about you, Blessing? Perfect. It's B. Yeah? So this one here is actually a carboxyl group, or a carboxylic acid. This one down here is a ketone group, right? Again, if we drew this out, this one would be a ketone. And this one here is actually a branched compound, yeah? So here, it'd be C, and there'd be 7C, so 1, 2, 3, 4, 5, 6, 7, yeah? And then here, we have this carbon here. So this is what this carbon represents. And here, we're going to have a branch off it, yeah? And then if we continue going with the straight branch, it's going to be this. So that's what this bracket means. The bracket means that it's branched off, yeah? So here, this is what this compound would look like. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this one would be decane, right? You don't actually need to know the name of that, but that's what this bracket actually represents. And this is what the compound looks like. Obviously, I've omitted the hydrogens because I don't want to draw 100 hydrogens, but does everyone get the point there? So this is just a branched alkene. That's what I'm trying to say. It's a branched alkene. Is that all good? Joe, Blessing? Slime shaking his head. Slime agrees. Okay. Which one of these represents an which one of the following skeletal formulas represents an ester? So which one of the following skeletal formulas represents an ester? A, B, C, or D? Oh, sorry, I didn't see your answers. I said it again. Send them again. Oh, wait, my bad. Let me look in the chat. Okay, yeah. See, okay, perfect. Do you agree with them, Blessing? Perfect. Okay. So here, so the rest of this part just has a bunch of questions here, yeah? And like we'll start going through some of these questions. It's just because the next part is very, very important, yeah? But we'll go through some of these questions. So we're going to try and speed run these. So here, a compound with the formula C6H12O2 has the following features. It is unbranched. It only contains one functional group. All carbon-carbon bonds are single bonds. Yeah? So it says here, which one of the following functional groups contains a nitrogen atom? Which one of these contains a nitrogen atom? Is it A? Is it B? Is it C? Or is it D? Send it in the chat. Answer B. Anyone else saying B? Yes, B. What about you, Joe? What do you think? Do you agree with them? Things B? Or are you gonna break the status quo? Yeah, you agree. Okay. So here it's B. Yeah? Which one of the following formulas represents an organic compound that contains two hydroxyl groups and had a molecular formula C6H12O2? So which one of these represents something with two hydroxyl groups that contains the molecular formula C6H12O2. Is it A, B, C, or D? What do you think? A, Storm says A. What about the other two? What about everyone else? A. What about you, Blessing? A. So we have here A. Yeah? Wait, no, it's not A. That's a bunch of lines. It's C, right? Read how many carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah? Wait, no. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. My bad, gang. So I counted the bottom one. I thought it was 14 carbons down there. I thought I was doing good at counting. I did not. So yeah, it's the answer option A there. So here, the compound C6H12O2 could be classified. Again, I put this context up here for a reason. Yeah, is it an ester, an amide, an amide, an alcohol, or an aldehyde? What do you guys think? Salam says C. What else? Anyone else? What do you think, Joe? What do you think, Blessing? C? Okay. C. All of you are saying C. This has one functional group to it. If it was C, yeah, you'd have to have two alcohol groups. So C's out. So did everyone say C because Salam said C? Or did everyone say C? I'm not insulting you, Salam. But I want to hear what the other. Why did
No,
you
I
choose
was
C?
focused on the carbon bonds, a single bonds thing.
Okay. So we've actually in the previous question we actually saw that here there had to be carbon-carbon double bond. This one had 14 down here. So it can't be C, yeah? Which other one could it be? Could it be an amide? What is required for an amide? Anyone want to shout it out? You can unmute, speak.
Nitrogen is needed for amide.
Yeah, so nitrogen is needed for the amide. And the aldehyde, again, you'd have to have two aldehyde functional groups to make up those two oxygens. So the only thing it could be here is an ester, yeah? Because ester functional groups naturally have two oxygens in them, yeah? Does that make sense? Any questions? Blessing, what do you think of this question? And I've lost her. Okay, wait, and she's gone. Okay. So I'll keep moving through it. Yeah. If anyone has any questions, always shout out. Like pause me, tell me to stop. If you don't understand it, shout out. Yeah. So here, yo, bro, you got. No, bro, I haven't even eaten breakfast. I'm just gonna say that now. I haven't eaten breakfast. Anyway, it says here, how many different functional groups can be found on this molecule? So what are the functional groups that can be found here? What can we see here? Right? How many functional groups can we see? Well, how many functional groups do you guys see?
Is it free or am I stupid?
It's 3, yeah. So it's B. Because we have the amine group here, right? We have a carbonyl group or a ketone group here. And then over here, we have a carboxyl group. Technically, if you want to be really specific, you can be like, actually, there's a carbonyl group and there's a hydroxyl group. But no, we don't consider that. We don't consider it. So the answer here is 3. Yeah. It's 3. This makes up a carboxylic acid. Any questions? Over here, right? What is the functional group labeled I? What is that functional group? Can you just type that name into the chat? I want everyone to give me the name. What do you guys think the name of this functional group is? What do you think his first name is? Because all their last names are John. Like for Jonathan. Yeah, that's it. This is an amide. So amide or amide linkage. Yeah, either one would be accepted. Probably call it an amide linkage because that's the more a proper name for it. Yeah. What about this one here? What is this one called? No. So Joe, this one's an amine. Yeah. So here, amine, amide. Yeah. Does that make sense for you? What the difference between the amide and the amine is? Is that all good, Joe? I low-key forgot. I know they both have a. So, but that's it, yeah. So, if we, dude, I wish I had my best friend. I wish I had a copy of my best friend. Let me just pull up my best friend. Why is it doing this? Why is it doing it? So if you look at the data book, I'm pretty sure the data book now just shows what the functional group actually is. So you don't need to memorize the functional group. You just need to memorize that your best friend has it in it. Yeah? So we go into 2026. We scroll all the way down here. All the way down. All the way down. And we can see this is what an amine has. It doesn't actually have amides in here. Mostly because we don't need to use them for naming conventions, but this has what an amine has. Yeah? We don't use them for naming conventions. They have all the naming convention stuff in here. You guys are so lucky. Back in my day, I had to memorize all this stuff. But now you guys just get to enjoy the fruits of my labor. Okay. And then what's functional group 3? What do you guys think functional group 3 is? I'm already getting cold. I'm only 2 years older than you guys. All I'm saying. So you're actually right here, Joe. This one here is a ester linkage. Yeah. Salam, what made you think this was a carboxyl group?
The oxygens.
The oxygens, yeah. So the big difference is you just need to be able to look at this final one over here, right? Because the final one doesn't have that H at the end, it's not a carboxyl. Because it has a C, right? It's an ester. So this is an ester linkage, yeah? Any questions behind that? Okay. What about you, Blessing? Are you understanding this?
Yeah, but my internet keeps on dropping out.
Okay. I'm gonna have to buy someone a new internet plan. So.
Yo, buy me a new internet. I need new internet.
So yeah, but aldehydes and ketones have the same molecular formula but different structural formulas and functional groups. Wait. Technically the same functional group. We just think of them as two different functional groups. Remember the aldehyde and the ketone group. Yeah. From the molecular formula, draw the structural formula of an aldehyde. Yeah. So how do you think you can draw the structural formula of the aldehyde here? Can someone describe it to me? Anyone?
Oxygen on the first carbon.
Yeah, so we can either have here, we can have the oxygen over here, right? Hydrogen here, hydrogen here, hydrogen here, hydrogen here, and hydrogen here. Yeah? I'm just going to say this now. This compound and this compound are the exact same as one another. Yeah? There's no difference, right? Because if I literally flip it over, it's the exact same thing. Yeah? It's me reflecting it. How about a ketone? How can we draw a ketone here? I'll get Joe to answer me here. What do you think, Joe? How do you think we can get a ketone here?
Probably O in the middle, I guess.
Yeah, so here we have the 3 carbons, and we have the O in the middle, yeah? Does that make sense? So, there's a bunch more questions in these slides here, yeah? If you guys just want to go through and have a go with them, right? That would be, that will help you guys a lot, yeah? Especially with the basic understanding of these things, because it just revises everything, yeah? The only thing that I would have to say is just talking about this one. So it says here carbon is able to bond to many different elements. The length of a carbon nitrogen bond is 147 picometers, whereas the length of a carbon hydrogen bond is only 109 picometers. Which bond would you predict to have a higher energy? Explain. So based on that information, which bond would you expect to have a higher amount of energy? A carbon hydrogen or carbon nitrogen?
I think hydrogen.
The hydrogen?
I don't know. That's what I think, because hydrogen bonds and shit. But
I think
So
nitrogen.
it will be the nitrogen one, right? So if I pull it up over here, yeah. So it will be the nitrogen bond because there's more energy required to keep that bond together. Yeah. So there's more energy required to keep the bond together. Hence, it has more energy in that bond. Does that make sense, Joe?
yeah, I wasn't reading the question. My bad.
No, it's all good. This is the hard question. So, question. Oh, what? Where are types of organic molecules? What? Yeah, but you guys get the idea. Okay. So I'll leave you guys to do the rest of these questions. Yeah, have a go with them, and this is just like this will give you like the best basic understanding or the base foundational knowledge of like what are these things? How can we use them? How can we understand organic molecules? And like what is the basis that we use that we base our organic molecules on? Does that make sense? So checking this. So we'll move on to the second part of this. Yeah. Which is going to be talking about the naming and properties of different bonds. So is everyone here, remember, homologous series, same general formula, similar structural formula. Yeah, I spoke about that already. Does everyone here remember what the dispersion forces are and the hydrogen bonds and the dipole-dipole are? Does anyone have any questions about those? Blessing, do you understand what those three are? Actually, would you be able to explain? If you can't, that's okay. Would you be able to explain to me what a dipole-dipole is? Like, how do dipole-dipoles come about? If you don't want to, that's okay. I'll ask someone else. Salam, do you want to tell me how a dipole-dipole comes about?
Um, Basically, it's just a stronger version of a dispersion force that's like it stays together instead of like a dispersion force. It stays and then it like breaks quickly or something.
Yeah. So you're going into a little bit of the technical side. So that's the idea of like how a dispersion force produces an instantaneous dipole, whereas a dipole-dipole force produces a permanent dipole. Right. The main thing is you just need to understand that the permanent dipole comes from the fact that we'll have we'll have a polar bond. So we'll have the change in electronegativities, yeah, which will produce our strong dipole-dipole forces, and then hydrogen bonds are just very strong versions of dipole-dipole forces. Yeah. So these are the three intermolecular forces. Don't confuse them with intramolecular forces, which are like the covalent, the ionic, the metallic bonds. Yeah. So intermolecular versus intramolecular. Does that make sense to everyone? Okay. So this is how we go about this is how we go about structuring our naming. Yeah. So the big thing that we want to focus on is identifying the parent chain. Yeah. So what is the parent chain of the compound? So here is 1, 2, 3, 4, 5, 6, 7. Or if we want to do the other way, we could do 1, 2, 3, 4, 5, 6, 7. Right? And the name of that parent chain is going to have the prefix hep to it. Yeah. So here, this one's heptane. Right? We'll focus on like the number of carbons and like their names in a second. But does that make sense to everyone? So that's the parent chain, yeah? We can either count it 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4. We can either do it backwards or forwards. Now, the reason they choose to do it forwards here is because of the other thing, the side groups or the branching, yeah? And the position of that branching. So here they've called it 1, 2, 3, 1, 2, 3 methyl, yeah? So here, this is a methyl group. We'll focus on the different types of groups. But I just want you to understand, why do we choose 3 here? Yeah? The main reason is because we want the smallest number. The IUPAC naming convention, or the IUPAC nomenclature, naming convention, nomenclature, they mean the same thing. Yeah? Requires you to use the smallest number. So here, right, if we put a 5 here, it's technically the same thing. Yeah? Like, because here on the 5th carbon of this chain, if we read it backwards, it's the same thing. But here we want to choose the smallest number. That's why it's 3. And here, the type of bond that it is, it's an alkane. So we end it with ane here. Any questions behind that? So these are the prefixes that we want to remember. Yeah. So here, methane is for one for parent chain of 1 length. Ethane for 2, propane for 3, butane for 4, pentane for 5, hexane for 6, heptane for 7, octane for 8. You won't have to go any higher than that. If they want you to go higher than that, they have to give you the name, right? What's so funny there, Joe? What's got you cracking? Those who know. What do you mean, those who know? Bro's gatekeeping a joke I don't even know. Do you get it, Salam? I'll ask Bashab. I'll ask Bashab about it afterwards. I'll give Bashab a message. Any idea? Any idea, Salam?
I think he's laughing at the 6, 7.
Okay. The other thing that we have to look at is our types of branching. Now, the data book actually goes through the different types of branching. But essentially, a branch will be identified by its length, right? It will be identified by mostly its length and its position. So here, this is called methyl propane, yeah, because it has a methyl branch here, yeah. So this is a methyl branch. This one here, it's a length of 2, so this one will be an ethyl branch, right? If we had a length of 3, that'd be a propyl branch, yeah. So if it was like 1, 2, 3, it'd be a propyl branch, right? If we had 4, it'd be a butyl branch. 5, pentyl branch, and so on and so forth. These are all in the data book, yeah? Any questions about that? Nothing? Give me a thumbs down if you have a question. These are the other types of things that we might have. So here, if it's a fluorine, we'll have fluoro. They're also identified with their position, and they're also prefixes. So we have fluoro, chloro, bromo, iodo, and these are also in the data book. So you don't need to memorize these more or less. Yeah, you just need to memorize the order that they come in. So these ones will always be prefixes. They won't be suffixes ever. We'll talk about suffixes in a second. So here, this compound, it's already kind of named it for you, but here, what would be the name of this compound? Does anyone want to take a guess?
2-chloropentane.
Yeah, so here it's pentane because it's 5, right? And it's also pentane because it only contains single bonds. right? And it has one chlorine group. So there's 2-chloropentane. And
Wait.
yes,
I forgot. When's the number in the middle again?
we'll deal with that in a second. So we're dealing with prefixes right now.
Okay.
Yeah? We'll talk about suffixes in a second. But you're right. We'll get to that soon, Joe. The only other thing I want to say, yes, spelling matters here. If you spell it wrong, you got the answer wrong. Okay, and the spelling's all in the data book. Please don't mess it up. This is the only time they care about spelling, right? We're not your English teachers. However, you still need to be able to spell. Okay. So here, if we have, let's just say, multiple different functional groups, yeah, multiple different positions, we could represent it with a tri or the di. Di, tri, or tetra. So for example, right, if we had F here, right? This basic by itself is methane, yeah? But here, we've replaced all of the hydrogens on methane for fluorines. So this is going to be tetrafluoromethane, yeah? If let's just say we had a C, and then C, right? This one would be like here, this is our main chain, and that's our side chain over here. This one over here would be 3-dimethyl, right? Wait, sorry. I'm really dumb. I'm really dumb. Wait, erase that off. Wait, if we had it 1, 2, 3, 4, 5, 1, and then 2, yeah? Here, this one would be called 1,2 dimethyl pentane. Yeah? Any questions about that?
Isn't it 2,3 dimethylpentane?
That's such an incredible point, Salam. Holy yeah, it's 2-3. I'm losing the plot. Any questions about that? So here, and one thing that I actually want to point out before we continue on is that here we can either count it as 1, 2, 3, 4, 5, or alternatively, we could count it as 1, 2, 3, 4, and 5. Yeah? And the reason being is because I can actually like think about it. If I turn this one, it will just look like this. Yeah? Yeah, that's what's gonna happen if I like sort of rotate this one. So here we need to really consider what is the parent chain, because they could have something that looks like this. Yeah? And here, the parent chain of this one, no one here is colorblind, correct? I'm drawing a different color. Okay.
I'm colorblind in 10 different colors. Sorry.
I don't know if you're joking.
No, I was joking.
So here, like for example, here, right? Most people would say it's butane, yeah. But here, if we use our right, like if we use the fact that we can use the right angle, so we have here 1, 2, 3, 4, and 5, yeah. It's actually pentane, yeah, because I can bend this one in such a way that it looks something like this. Does that make sense? Any questions, Blessing, Joe? Because I can see Salam's face. He's like nodding. Okay, no questions. Wait. So wait, does that mean you do have a question, Blessing, or you don't have a question?
No questions. I just think it's stupid, but yeah.
What do you mean you think it's stupid? What part of it?
Don't worry about it.
Like how they represent it like this, and like how it looks like 4, and when it's really 5.
Yeah.
Yeah, no, but think about it like this. They're trying to trick you in any way, shape, or form. Remember, in electrolysis, water is always messing with you. Obviously, because I'm recording this, I can't use the phrase I would use in a tutoring session. But you guys all know that phrase. So, here, right, it's asking us, before we begin this, yeah, I want to talk about the naming conventions for double bonds. Right? Because we've been dealing with mostly single bonded compounds, right? So here, we have here CC, and this is what the compound looks like, yeah? So this is hydrogen. I mean, not hydrogen. This is carbon, yeah? So this here is going to be ethene, yeah? This is ethene, yeah? The ene represented has a double bond, yeah? So ethene. So here, down here, we have 1, 2, 3, 4, 5. Is that methane? Will that be the prefix meth? Eth? Prop? Bute? Pent?
And
It'd be pent? Does everyone else
yeah,
agree with that? Perfect. So it is pent, yeah? So this is called pent. Pentan 1, because here the double bond is on the first carbon. Ene, yeah? Pentan 1 ene. Does that make sense, Joe? Where we now use the double.
yeah, yeah, yeah.
So here,
Hey, I'm just a little washed. It's okay.
it's all good. It's all good. That's why we're doing this.
It's all coming back to me.
So, here's the priority order stuff. So we'll start off with this slide. This is the lowest priority order, and this is the highest priority order. We basically name it based on the priority order. The priority order is in the data book. There is no reason for you to not know this, yeah? But the priority order is in the data book. They won't get you to name amides. So, for example, here in the data book, they don't have amides, so they won't get you to name it in the exam, yeah? But here, I want you to remember these. If you don't remember them, I'll be very disappointed because they are literally in your best friend. And all of you should have your best friend on you at all times. What's your best friend again, Joe?
Oh, my calculator, because I hate my data booklet.
What's your best friend, Salam?
My data book.
Okay, good. Joe, speak to me after this, bro. You gotta pick which calculator. Is
Oh.
it the scientific or is it the CAS?
Not the CAS. The CAS too complicated.
Okay. Bro, next to that, dude, I'm just gonna start using an abacus. I'm gonna start using an abacus in tutoring session, so you have to use so you have to use the freaking so you have to use the data book instead. Start counting with an abacus. Anyway. What was I saying? Oh yeah, so this is the priority order. Basically, the highest priority is a suffix, right? So it goes at the end, and the lowest priority is a prefix. Obviously, we'll like do some questions on it before we like have to like deal with it. So here, this molecule, yeah. So this molecule here has 5 carbons, yeah. So we know it's a pent, right? That's what the parent chain is. We'll just check it real quick, right? See if we can like if we twist it or turn it anyway. So here. Like if we start here, 1, 2, 3, 4. No, that's 4. So that's too small. Yeah. So here it's going to be a pent, right? Here, right? This one, like, this is like now we're trying to pick the priority order because technically we can count it as 1, 2, 3, 4, and 5. Yeah. But the thing is, we want the suffix, right, to have the lowest priority order. Yeah. So here they have here. The double bond here, which is going to be the suffix of this, yeah, because it's the highest priority order. Again, if I look at my data book here, this is a higher priority order than halogens. That will always be the case, yeah. So if we go back into here, yeah, that means we're going to count from 1, 2, 3, 4, 5, yeah. So this has the lowest number to it. We want the suffix to always have the lowest number. So this one's going to be 3, 4. So 3, 4 dimethyl pentan 2-ene. Does that make sense for everyone?
Wait, I'm a little confused because on the second like branch, it's connected to 2 C's. Wait, what's the difference between this?
So this one here, yeah. So you actually make a good you actually make a good point, Joe. Yeah. So over here, right? We can technically count it as 1, 2, 3, 4, 5, or 1, 2, 3, 4, and 5. Yeah. Is that what you mean?
Yeah, but like, okay, why? Like, okay, you know how it's dimethyl?
Yeah.
Like but the second chain's connected to two C's. So does that make any difference, or for the side chains? I mean, yeah, for the branches or not?
So like two separate C's.
Yeah, because the second branch is connected to two other C's.
Oh yeah, yeah. So that means we just pick one to be a part of the main chain, yeah, and the other one has
Oh,
to be a side chain. So here you can technically have it as 1, 2, 3, 4, and 5, or we can have it as 1, 2, 3, 4, and 5. Yeah.
all right.
So both of them work. Yeah. So you're not wrong. Yeah. We just
Yeah,
pick
yeah.
one to
Alright.
be a part of the main chain because I don't really want to say 1, 2, 3, 4, and then we have what's it called? 1, 4, 4 trimethyl. Yeah, we want to try and reduce the amount. Does that make sense?
Yeah, that makes sense.
So you're absolutely right. And I'm just gonna say this now. If you write it with the prefix in the front, I swear to God, right? Like sure, the VCE will write this in the multi-choice. That's why I have this note up here. Yeah, but please don't do it on your actual exam. I'm begging you. Yeah, on your actual exam, just use the IUPAC naming convention that we're all used to. Yeah, so it's gonna be, as I said, the 3 comma 4 dash dimethyl pro pentan 2-ene. Any questions about that? Okay. So, what is the IUPAC naming convention of this? I will do this one, yeah? Because this one's a little bit of a trick. So here, right, we have a functional group. The functional group always has to be on the main chain, yeah? All functional groups have to be on the main chain. So despite the fact we can get here 1, 2, 3, 4, 5, 6, 7, which is longer than the 1, 2, 3, 4, 5, 6, the functional group always has to be on the main chain, yeah? So here, right, we're going to have 1, 2, 3, 4, 5, 6, yeah? So that means this is going to be a hex molecule, yeah? And there's no double bond, so we should expect hexane, yeah? So the main chain is a hexane, yeah? Over here, we see two branches, yeah? One's a methyl branch and one's an ethyl branch. So here, right, we also do an alphabetical order. So we see here, this is going to be 2 sorry. So the beginning of this prefix is going to be here 2 ethyl 3 methyl. Yeah, so we're doing this in alphabetical order. We're writing this in alphabetical order, right? So that's what's going to be the prefix of the front. Now, how do we describe this oic acid group? Yeah, essentially we end it with oic acid, right? So we replace the E in hexene, so we get hexane oic acid. Yeah, so if we combine these all together, we get 2 ethyl 3 methyl hexane oic acid. Does that make sense? What about for you, Joe? What about you, Blessing? Does that make sense for you? So functional groups has to be on the main chain, and it needs to be in alphabetical order. Yeah. And the reason I pick this as the highest priority is because it's at the top of the thing. Yeah. So highest priority, lowest priority. Let's go back here. So here, right? This is the naming convention of non-branched esters. So I want to talk about this with you guys. So here, right? Esters will have two parts to it. They'll have the al. They'll have this al part at the end of it, and they'll also have an O8 part to it. Yeah. So here, right? The al part is whatever doesn't have the double bond, the carbon oxygen double bond. So that's going to be this part over here. Yeah. So it doesn't have this part to it, this part over here, right? So that means this is the al part. This is going to be propanal, yeah? So propanal, yeah? This second part is going to be named based on whatever the main chain is here. So this is butane, this is butanoate, yeah? So this is propanal butanoate. Does that make sense to everyone? So we have two parts, the al and the O8. The al is going to be what doesn't have the double bond. The O8 is going to be the thing that does have the double bond. Does that make sense? Okay. Wait, Joe, do you have a question about that? You were like, you had no, okay. The emoji. So here, this one. What is the correct IUPAC naming convention here? So here, is it A? Does anyone think it's A? Any takers for A? Salam says A. What about everyone else? Joe says A. What about Blessing? What does Blessing say? So the two of you are right. Yeah, it is A. Yeah. Most people. So it's obviously not B because there's three carbons there on the main chain. Yeah. Here, it's not 3. Yeah. Because because if it was 3, we'd be counting as 1, 2, 3. But we want it to have it the lowest number it can. Yeah. So it's the lowest number that it can. It needs to be the lowest number. Alphabetical order, lowest number. Yeah. So the suffix must always have the lowest number that it can. So here, which one of the following is the correct systematic name for the compound with the semi-structural formula CH3, CH2, CH3? So can someone tell me how I draw this one out? Because we can't really do anything with this. Joe, do you want to try and help me draw this one out?
First carbon with 3 H's on the sides. Second carbon with 2 H's on the side. Carbon with 1 H on the side and the other C. Yeah.
Like this?
And then and then CH3. Yeah.
So
I don't know.
Remember, all carbons have 4 bonds to them. Yeah. Do all these carbons have 4 bonds?
No, but how do I connect them to get 4 bonds?
This has to be a double.
Oh yeah.
Does that make sense?
Yeah.
Does it make sense for you, Salam and Blessing? Okay. So here, right? What is this going to be? Is this going to be but or is this going to be pent? Anyone want to shout it out?
And
And 2-teen.
Yeah, it's going to be pent. It's going to be pent-2ene. So it's definitely not this. And it's not 3 because we want the lowest priority order. Yeah? So the big thing, read it both forwards and backwards. Yeah? So now this I've cut off part of this. Let me put the H back on here. But here, this whole figure is describing the idea of a structural isomer. Yeah? And what is a structural isomer? It has the same molecular formula, different structural formula. So all of these things can be represented as C5H12. Yeah? All of these things, you can count it yourself. All of these things are C5H12. Except, right, they're drawn in slightly different ways. Yeah? So here, this C5H12, it could be pentane, but it could also be methyl butane, but it could also be dimethyl propane. Yeah? And here, they need to give you more information if they were to get you to draw a structural formula. You cannot, absolutely cannot, base your understanding by the fact of the molecular formula. Because the molecular formula could have multiple different isomers, right? That's the phrase we use. Isomers, and more specifically, structural isomers. We have different types of isomers that we deal with. Yeah? So these ones are structural isomers. Later, we'll have functional isomers and optical isomers as well. Yeah? Does that make sense? Any questions from you, Joe? Blessing? I'm just being aired out by Blessing right now. My heart's broken, man. Anyway. So, we'll go to here. So how many different structural isomers are there of C4H9Cl? Does anyone want to try and take a guess, or does anyone want to have a try go at this question? Or I'll leave it to the floor. Does anyone want to have a look see? What do you think, Joe, or Salam, or Blessing? Anyone?
Is it 4?
2, 2, 3, 4, around there. Yeah.
Was 2, 3, 4? Okay. So, to figure out the number of structural isomers, you have to you have to draw them all out. Sadly, that's the annoying part about structural isomers. Let me put my pen in the right one.
1, 2.
So here we have C, 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 C. Yeah. So this basically this will all look the same. It can either be Cl here or a Cl here. Those are the two possible options. Yeah. But we could also have C, 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 C. Yeah. So there could be a Cl here or a Cl here. Do you see how if I put the Cl over here, it's the same thing as me putting the Cl over here? Yeah.
Uh, 9 H.
Does that make sense?
Can't you put the Cl on the branched carbon as well for another isomer?
So technically, that would mean it's like here. Then we could count it as 1, 2, 3. So it'd actually be on the parent chain then. Yeah.
Yeah.
So do you understand how there's 4 here?
Yeah.
And so any questions about that? No one? Nothing? Okay. So here, the compound that is not an isomer of 2,2,4 trimethylpentane is. Which one of these is not an isomer of 2,2,4 trimethylpentane? So you might have to draw this one out. Yeah. So what is Joe? How would I draw this one out?
What? 5 C's, 5 carbon chains in the middle.
Yeah.
And then you got 2, 2, 4 trimeth. What? So add C on the 2.
Yep. So you can add the C here, the C here.
Yeah. And then I add a C on a 4.
Yeah. So and then here I draw out all the hydrogens as well.
Yeah.
So here, what is going to be the molecular formula? Any ideas? Anyone want to try and guess the molecular formula for this?
C8H18.
So he CHH18. Yeah, pretty sure that's right. So that means we already know octane is an isomer. Yeah, so octane's correct. What about 3 hexane, three hexane. Is that the answer? So is that an isomer or is that not an isomer? That's what I'll ask. So just message in the chat. Do you think it is or is not? Put thumbs up if it is. Put thumbs down if it's not. So Salam thinks it is. What about everyone else? Does anyone else think it is an isomer? Yeah. What about you, Blessing? What about you, Cav? Cav thinks it's an isomer. Okay. So yeah, this one is an isomer. What about C? Is C an isomer? Yeah. Down from Salam. What about you, Joe, Cav, Blessing? What do you guys think?
I don't know.
Mature? So Cav doesn't think it's an isomer either. So Joe, how would you draw this one out? I'll ask you. How would you draw out C? Hello, Joe?
What? 5 C's and then 2. There's a C at 2 and there's a C at what 4? Yeah.
So is that enough carbons for this?
Hmm.
Is it enough carbons for this to be an isomer of this?
Nah.
Yeah. So the answer option is C. So Kevin Salam, right? Yeah. Any questions about that at all? No, the best way to figure
No.
out isomerism is to literally just draw it. Yeah. So melting point and boiling point are influenced by the three forces. Yeah. Dispersion, dipole, and hydrogen. Yeah. That's all I really want you to take away from here. Again, they're intermolecular forces, not to be mistaken with intramolecular forces. Yep. So here, dispersion forces, right, can be increased by increasing the length of the carbon chain, by reducing the branching, and by increasing the saturation. So I'll explain this one. So essentially, right, what I mean by that is that let's just say we have CC. So let's just say we have ethane. Yeah, this molecule here is ethane, and I compare that to let's just say we compare it to propane. Yeah, here propane is actually going to have stronger bonds because it's the longer carbon chain. Yeah, does that make sense to everyone? Like, think about it. If they're longer chains, they can sort of attract a lot stronger to one another. Yeah. However, right, if we have that's about the length. So as the length increases, so does the strength of the forces increase. The reducing the branching, right? Let's just say we have here this is butane. Let's just say this is butane. I'm not going to draw the carbons, yeah, because the carbons are a bit of pain. And over here is methyl propane. Yeah. Methyl propane is going to have weaker forces than butane is because it has a higher level of branching. This is the reason being is because it can't pack nicely. Yeah, it can't pack nicely together. Yeah, and because it can't pack nicely together, right? It's going to have weaker dispersion forces because if it can't pack nicely, it can't produce those nice forces between them, right? Same thing with the longer chains. If you have the longer chains, right, and they can pack nicely, right, you have more places for those dispersion forces to exist, hence increasing the strength of the dispersion forces. And then increasing the saturation. So this is like essentially, remember the kinky chains that we were talking about? So if we have it, the C double, like here if we have propane. Okay, yeah, I see you laughing this a lot. I see you, boy. So here if we have propane compared to propene, yeah, propene is going to have those kinks in the chain, which means it can't pack nicely. So do you see I'm going back to this idea of it packing nicely or packing efficiently? Yeah? Because of those kinks, it's going to be bend. So like a propene packing is probably going to look something like this. Yeah? Where it can't like pack very nice is going to look like this. But propane is just going to be nice linear chains. Yeah? Because it doesn't have any of those kinks in them. Yeah? So I'm focusing more on like just understanding how these forces work. And these are the ways we can increase the strength of dispersion forces. Yeah, Bo's still laughing. I got Bo cracking up. Okay, I'll stop. I'm not picking on you, Sam, I swear. So, here, the permanent dipole-dipole interactions, that's just about having something that's high in electronegativity bonded with carbon. So here, right, the functional groups that we'll see with dipole-dipole forces are going to be the aldehydes, the ketones, the esters, and the halogens. And it's simply because the delta H here, because of this delta positive, delta negative that's occurring between them, yeah? Which causes there to be a permanent dipole, right? That permanent dipole causes these dipole-dipole attractions to occur, yeah? Now, one thing I'm going to say, just because dipole-dipole interactions occur, that doesn't mean that there were no dispersion forces. When we have, like, let's just say, like an aldehyde will have the dispersion forces as well as the dipole-dipole, yeah? So they like sort of layer on top of one another. Any questions about that? Okay. So then we have here the hydrogen bonding. Now, for someone in here, so someone needs this lesson. We have here a noft bonded to a hydrogen bonded to a noft. Yeah. So, what this means is that if a nitrogen, oxygen, or fluorine is bonded to a hydrogen, and that hydrogen is bonded to a noft, a fluorine, and a hydrogen, both intramolecularly through a covalent bond and intermolecularly through a intermolecularly through that hydrogen bond, right? It's going to produce what we call a hydrogen bond. Yeah. So here, if you have an O bonded to an F, a O bonded to an oxygen, a hydrogen, and that hydrogen is bonded to another O, that's going to be a dipole-dipole. It's going to be a hydrogen bond. Yeah. And it's a specialized type of dipole-dipole. So that means here it's going to have, like, for example, an alcohol is going to have dispersion. It's also going to have those dipole-dipole forces, but it's also going to have hydrogen bonding on top of it. And as we increase, right, dispersion is weaker than dipole, which is weaker than hydrogen. So hydrogen's our king, yeah? Hydrogen's the top. Does that make sense to everyone? So like, for example, with an amine, right, we'll have here like CNH, H, and we'll have here like CNH, H. These hydrogens, if they bond here, they're going to produce dipole-dipole form. Hydrogen bonding, yeah? Because they're covalently bonded to a noft and intermolecularly bonded to a noft. Any questions about that? So, how do these affect the boiling points, right? So, as the bond strength increases, yeah? So, if we have, like, we're comparing a compound like, let's just say, I'll pick something really simple here. We'll pick here methane compared to methanol, yeah? Methanol is going to have a higher boiling point, or you'd expect it to have a higher boiling point because of the fact it can produce more dipole-dipole forces. Or actually, can produce stronger intermolecular forces. So, does that make sense? So it can produce those stronger intermolecular forces. Yeah? The same thing, right? So you'd expect it to have a higher boiling point. If we, let's just say, compared methane to something like, let's just say, we'll draw out a really big compound here. Yeah, very big, I know. You don't have to tell me. I have great understanding of size. Yeah? So if we compare methane to butane, yeah, butane, because it produces those stronger dispersion forces, it's going to have a higher boiling point. Yeah? If let's just say it was butane compared to, let's just say we have here butene or butene, yeah? That's here. Butane is going to have the stronger, is going to have the higher boiling point because it can produce stronger dispersion forces. Because remember those kinks in the chains in the butanol, they make it produce weaker dispersion forces compared to butane. Does that make sense? Any questions for that behind that for anyone? Because I can repeat that.
Does that mean alkanes have higher like boiling and melting points than alkenes in general?
Yeah, in general, usually what they do is they try and make the compound as similar as possible. So, like, for example, I compared a butene with a butane, yeah? They won't get you to compare, like, octene and, like, butane with one another, yeah? They're only going to have, like, one difference. And the one difference is probably, does it have this type of bonding? Or, like, what type of forces can it produce? Or, like, how long is the chain? So they'll compare, like, alkenes to alkenes and alkanes to alkenes, yeah, but they won't compare them like, oh yeah, here's a different length molecule with this and like with a double bond, and here's this molecule that's an alkane. They won't compare it like that. Does that make sense?
Yeah. Okay. Thanks.
Any other questions for anyone? Okay. So here, which is the strongest type of attraction that exists between the molecules of this substance? So between molecules, yeah. So is it A, B, C, or D? So does anyone think it's A? Give me a thumbs up if you think it's A. Thumbs down if you think it's B. So I'm seeing a lot of thumbs down. Thumbs down. Yes, thumbs down. Yep, perfect. So it's not that. Is it B? Do we think it's B? Okay. So I'm seeing mostly thumbs down. There's one thumbs up. What got you to pick the thumbs up, Kavini?
Structuring. I thought that you can't build a H now, but I'm guessing you can.
So so here we have this carboxyl group, yeah?
Mm-hmm.
And with that carboxyl group, what is going to happen is we'll have this, like for example, we have like another one up here, yeah? OH, yeah? Do you see how that can produce, it's covalently, the hydrogen's covalently bonded to enough and intermolecularly bonded with enough?
Yeah.
So that's why it's actually C. Yeah. I swear, if anyone picked D, I was actually going to explode. Because remember, it's the forces between molecules, the intermolecular forces, compared to the intramolecular forces, the forces within a molecule. Yeah. So intra within.
Yo,
Yeah.
if I pick B, how long does it take for you to explode?
Alright. Funny guy. I probably wouldn't explode if you picked B. I would say like B's understandable. B's just like a no-go. Yeah. It's like
Yeah,
for
yeah.
example, they
I'll
have
pick
like
C. But
have you guys ever done those modules where they're like, oh yeah, like how do you treat Betty? Like how do you make sure Betty gets the assistance that she needs? And like one of the answer options is like, yeah, it's not your problem, you don't have to deal with it. The second answer option is like, oh yeah, just tell her to get over herself. The third answer option is like, the third answer option would be like, yeah, force her to do something. And then D is like, make sure you encourage her lovingly to approach the appropriate medical services required. Yeah, that's what I've been doing, right? That's what I've been doing with my spare time. That's the type of shit that we do in med school. It's so bullshit. It's so stupid. Anyway, we'll go on to this one. Consider compound 1 and 2, which are saturated that contain the same number of carbons. Yeah. Which one of the following gives the compound which one of the following gives the compound expected to have a lower boiling point and why? So which one do you guys think? I think it's A, B, C, or D. Put it in the chat. What do you guys think? D. Anyone else? What about you, Joe? What do you think? Think it's D? Yeah, it's D. Again, it's this idea of this one packs a lot more efficiently than that. Like at what? Well, okay. If you guys have seen oh, actually, we won't go there. Yeah, but here, imagine packing a bunch of hexagons. Like here, you have one hexagon. You know, here you have a second hexagon. Right? It's gonna be a bit of a pain in the ass to pack together. So, any questions about that? There's none. Put thumbs down if you don't have any questions. Okay. Viscosity, right? The definition of viscosity is the ability to resist flow. Yeah? So resist flow. Yeah? If it resists flow, that means it has stronger bonds it needs to overcome. Yeah? So the stronger the bonds, the more viscous. So you can think about water compared to honey. Yeah? Water flows a lot more easily. Or like if you like scoop out honey and scoop out water, and then you try and like pour them both into a sink, you can try this at home if you want. I don't know if your parents are gonna yell at you for wasting food, but like if you pour them both, you'll see that the water flows very quickly and the honey goes very, very slowly. Yeah. The reason that occurs is because the honey is more viscous. Yeah, it has stronger bonds that it needs to overcome. Whereas the water, if you pour it out, it just floats. Yeah. So any questions about does that idea of viscosity make sense? So essentially, the stronger the bonds it has, the more viscous it is. Yeah. So here, again, if I compare my methane to my methanol, yeah, you'd expect methanol to be more viscous because it has stronger intermolecular forces. Yeah. And then as it says here, right, viscosity, as the temperature decreases, the viscosity increases. As the temperature increases, the viscosity decreases. So that's just something that you need to remember with viscosity. That's completely out of which is completely unrelated to everything else we've discussed. Yeah, but that's just something like think about it. If I heat up like if you guys have ever tried to heat up honey and then like watch it like run, it's a lot faster than like cold honey. I don't know. Don't try that at home. I don't know if your parents are gonna yell at you or like if you're gonna light your house on fire. Please don't light your house on fire. Okay. It's a lot of money. So here, which one of the following correctly lists? Which one of the following correctly lists these compounds in order of decreasing ability to flow? Yeah. So decreasing ability to flow. Does that mean it's more viscous or less viscous? What do you think? More, put your thumbs up. Less, put your thumbs down. Yeah, so less, so decreased ability to flow means it's more viscous, guys. Yeah? So the ability for it to resist flow, viscosity is the ability for it to resist flow. So that means here, if it's like, it's actually increasing in viscosity. Yeah? So here, the one that decreases its ability to flow, the order here would be 1, 3, and then 2. Yeah? Does that make sense? Any questions about that? I saw you pick B, Cav. It's incredibly rough because it says decreasing ability to flow, so the more viscous. Yeah. Does that make sense? Okay. So here, right, we're about to run out of time. But again, there's more questions at the back here, right? I just have a shit ton of these questions. And we've essentially done the entirety of the basics of organic. Yeah. Tomorrow, what I'm planning to do is I'm planning to start doing the organic pathways stuff. Yeah. So there's a lot of stuff in the organic pathways. But how's everyone felt with today? Has everyone felt today was useful? Has everyone thought that today was useful revision on organic chemistry. It refreshed my memory a bit. Okay. I would recommend go back and do do questions, Joe, if you want to like keep that memory. Yeah. If you want afterwards, I can see if I can have a look around for some extra questions if you guys want, just to continue like reviewing your memory, revising. I'm also going to put these slides on my website, so if you guys want to see these slides, you can. Yeah. Is that all chill with everyone? So I'll just finish off the day by doing these two questions here. So how many carbons are on the parent chain? What do you guys think? A, B, C, or D? What do you guys think? A, B, C, or D?
B.
So Joe says B. Does anyone else agree with Joe? Kavinu disagrees with Joe. What about Salam? What do you think? You think it's B or C?
C.
C. So Joe, my guess is that you counted at 1, 2, 3, 4, 5, 6, 7. Yeah? However,
Yeah.
remember, if we turn this one this way, we can actually count it as 1, 2, 3, 4, 5, 6, 7, 8. Does that make sense? They're trying to trick you. They're trying to trick you, right? So here, which option represents the correct lowest cumulative position and name of the branch? Yeah. So which one of these has the lowest position? Like, which one of these describes the lowest position? So, is it going to be A, B, C, or D? What do you guys think? Also, I cut out the hydrogen by accident. My bad. I should probably like make sure I hit this out. So what do you think? A, B, C, or D? Type it into the chat. B. What else? B. Okay. So I've seen 2 B's. What about Cav? What do you think it's? What do you think it is, Kavina? So here, the answer is B, yeah? Because here, 1, 2, 3, this is the third carbon, yeah? So the methyl group is on the third carbon, and the methyl group is also on the fifth carbon as well, yeah? It's not A, and it can't be D, yeah? If you picked A, there'd be only one group, yeah? And you can't pick D here, because there's actually no ethyl group here. You would have gotten D if you did the previous question wrong, yeah? Here, right? C is technically correct. However, we always go from the lowest number. Yeah. So the lowest number, we want the lowest priority order. Yeah. So, and then last thing, what do you guys think the IU pack name is? Write it down. Write down what you think the IU pack name for this is. I cramped my side. So, out of the two that I've seen there, yeah. Do you agree with that name, Joe?
Yeah.
So here, out of the two, which one do you think is the more correct one? Because there's mistakes in both of them.
Close alarms, except for the fact that he doesn't have a comma.
Yeah. So here, it's 3,5 dimethyl, no spaces, octane. Yeah. Oh, why is bro analyzing my typing? You do like you can't put any spaces on the exam. No. You I'll be so like you can't put spaces in. Like I'm not doing this to be picky. This is like how they do it in the exam. So here it's 3,5 dimethyl octane. One word. Yeah. So I'll end it off there for you guys. Yeah. How have you guys found today? No, am I just gonna get aired out? Alright, okay. You guys can.
Bro, you just glitched out for you.
Oh, did you? Okay. My bad.
I didn't hear nothing you had said for the last minute.
So, no, it's all good. It's all good. You guys can head off then. If you have any questions, stay back. I'll be here for like 5-10 minutes. And for anyone doing the methods one in an hour, I'll see you there.
Alright, see you, bro. I'm gonna go eat some spring rolls.
Alright, bro. Enjoy the spring rolls.
Thank
Right. Do you have any questions?
Yeah, I'm gonna need you to explain that viscosity.